thermodynamics and heat transfer. For our first problem, for our part 1 problem, we have a thermal efficiency and power output of a gas and turbine are given. The rate of fuel consumption of the gas turbine is to be determined. So, the thermal efficiency and power output of a gas turbine is that 0.8 cubic centimeter and 42,000 kilojoules per kilogram of power output. Let's proceed. The gas turbine is converting 21% of the chemical energy released during the combustion process into work. The amount of energy input required to produce a power output of 6,000 kilowatts is determined from the definition of the thermal efficiency. So, the amount of energy input that is needed or required for us to produce a power output of 6,000 kilowatts is this: 28,570 kilojoules per second. This is the amount of heat energy that is needed in order for us to produce 6,000 kilowatts of power input. To supply energy at this rate, the engine must burn fuel at the rate of 0.6803 kilograms per second. This is our mass flow rate, or this is the amount of fuel needed to be burned in order for us to produce this input energy. Since 42,000 kilojoules of thermal energy is released for each kilogram of fuel, then the volume flow rate of the fuel becomes 0.6803 kilograms per second of mass flow rate divided by the density, 0.8 kilograms per liter. We have a volume flow rate of the fuel, 0.850 liter per second. So in order for us to produce a higher efficiency power output, we need to burn a fuel at a rate of 0.6803 kilograms per second. So, it is the amount of fuel released during the combustion process. And this combustion chamber produces an amount of work that is 28,570 kilojoules per second supplied into our heat engine, and the other are wasted into the sink and released or produced using our 21% thermal efficiency. So that's all for our part 1 problem on the reactive systems of thermodynamics and heat transfer.